with the right hand. Okay, so this is the next question that we have on the menu today, and it's presenting us a situation where we have Jane, who is 50 kilograms, needs to swing across a river filled with crocodiles and velociraptors. Dinosaurs are coming back, and she's trying to rescue Tarzan. And Tarzan is a little bit heavier at 90 kilograms. So she must swing with a constant horizontal wind force that is applied to her. Oh, this is the diagram that represents it. So as Jane starts here and she swings over, the wind is trying to blow her, you know, the wind is working against you. Working against Jane in this case, as she's swinging there. And it's initially set at an angle theta with the vertical. Theta is given as 50 degrees. And we also have a couple distance vectors or values. So the separation of the river, 50 meters, and the wind force is 150 newtons, and the length of the rope is 40 meters. Okay, cool. So let's draw out the situation. Let's actually think about this question first. So what is the minimum speed that Jane must begin her swing with in order to make it to the other side? And the hint that we're given is that we gotta work with energy, which is cool. I always feel energized with the energy, nothing to be worried about. Okay, cool. So let's redraw this out in a more abstract way. So we know that we have situation comes to us like this. Here we have theta, which is 50 degrees. This length here, we have L. That was given as 40 meters. And that starts up here. Jane is 50 kilograms. And coming this way, we have a different angle. Here they represent that with the letter chi or phi. Now, I don't think we're given phi. Yeah, I don't think we're given phi, so we'll probably need to calculate it, which is nothing to be too worried about. Okay, no worries. And here we got Tarzan. Let's just say TZ. Tarzan from Tanzania. The Tarzan was 90 kilograms. The distance between them here is 50 meters. Okay, so the first thing that we're going to need to consider here is that we do have an unknown height difference that we definitely need to take care of. So this is H. Now, we do need to do a little bit of trigonometry to figure out what in the world that is going to be. So if we look at this diagram right here, we could figure out, knowing the hypotenuse, what this distance is with some trigonometry. So that is going to be 40 meters times cos 50. And we know that 40 meters is going to be h plus this distance right here, because that's going to be the swing. Yeah. And oh, this should be like from the base, because we're going to come up a little bit as we get back to Tarzan's side. So this, maybe just to be 1000% clear, I'm gonna just redraw this like this. Lowest point of swing. Okay, cool. So we know that 40 meters, which is the length of the 40 meters is the length of the rope itself, and at its lowest point. And at its lowest point, it's going to be this height, which is 40 cos 50. Don't really need the units here. Plus h. Okay, so isolating for h, we're going to have h is equal to 40. Factored out the 40 is going to be 1 minus cos 50. 1 minus cos 50 degrees multiplied by 40 meters. We got 14 meters. 14.3 meters. Okay, this will be our h value. Now this h value here is going to be useful. Okay, it's actually a fairly tough question. Okay, so we're going to follow the same procedure on the other side to find this angle right here, because that's going to be quite important, because we need to know, like, not just the distance between them and the ground, we need the distance between them and each other, or not the ground, between them and the lowest point. So if maybe I'll do that in a different color. Let's do green. Okay, so this height here, let's call this HT, height of Tarzan. So height of Tarzan is going to be L minus cos chi L again. Not chi, it's phi. And so this shall be, now we don't know phi right now, so we're going to need to leave that, but it's going to be 40 times 1 minus cos phi, like that. Okay, now for these distances, so maybe I'll do a different color for this, perhaps blue. So let's call this dj for the distance between Jane and the lowest point. And here we're going to have dt for Tarzan's distance. Okay, and those are just going to be trigonometries as well, except we're going to use sine instead. Okay, so dj is going to be equal to 50 sine 50 times L, which is 40 meters. Okay, so I'm going to calculate that real fast. Sine 50 times 40. 30.64 meters. Okay, and dt, the distance between Tarzan and the center in the lowest is going to be, well, is going to be sine phi times 40. Times 40. And we don't know what phi is, but we know that 50 is the sum of dt plus dj. So solving for dt, we know that this is going to be equal to 50 minus 30.64 meters. And that will be equal to sine phi times 40. So phi will be equal to 50 minus 30.64. So I'm going to do that real fast. $19.36 over 40. Oops, all of those need to be passed to inverse sine. Or arc sine, if that's more your style. It's probably more safe to say arc sine. Okay, so arc sine of 19.36 divide 40 is equal to 20. Oh, I have the distance, but I need the angle. So I need to inverse sine that. Oh yeah, it is 28 degrees. Or 29 degrees, just to round it. Okay, so let's put these onto our diagram. So here we have 30.64 meters. dt it's going to be 29.36 meters. H is going to be 14.3 meters, and HT, now that we have phi, we can calculate that. So let's go back to green. One minus cos 29 degrees calculating that ASAP fast. So here I got h of t 5 meters. Okay, so I'm actually going to redraw this diagram ASAP fast because actually no, I think we're good. So this will be 5 meters. Okay, so as we can see, if Jane just swings here, she's gonna go as far as she can. like she's gonna gain a lot of kinetic energy because she's gonna end up lower than where she is. But keep in mind, we have a constant wind force going this way. So Fw for F wind, and that is equal to 150 newtons. Oh, you can't even see that I was writing. Okay. So here, F wind is equal to 150 newtons. Whoops, not W's. Newtons. Okay, and we know that the work done by wind is going to be 150 newtons, because it says it's going to be constant, and we're going to multiply it by the distance at which it's going to be applicable, right? So it's going to be for 50 meters. So 150 times 50 meters is equal to 7,500 newtons. Joules of work. Okay, so that's the work of wind. Okay, so now that we have all of these, now that we have this diagram complete and all the work and all that, we can kind of start moving towards actually calculating Jane's journey and what we should do in response to that. Okay, so as you can kind of see from the diagram, as Jane goes down, like she's going to lose some height, and because she's losing height, she's losing gravitational potential energy, and she's also gaining kinetic energy as that happens. Now the energy, another thing that we kind of need to keep in mind is that once she arrives to the other side to rescue Tarzan, she's got to have a velocity of 0, otherwise she's going to like kick him in the face. Like she's hopefully going to try to get there with a velocity of 0. So we're basically looking for the kinetic energy of Jane plus the kinetic energy gained from the gravitational by reducing her height and on that swing. That has to be perfectly balanced with the work of the wind to make it so that her energy as she gets here is going to be a 0, or her velocity as she gets there will be 0, so no kinetic energy. Okay, so let's set up that equation like this. So conservation of energy is our key concept. So we have our initial kinetic, so KEI for initial, plus our potential energy initial is going to be equal, or it's actually going to be our change in potential energy, because up here you're going to have a certain degree of mgh of potential energy, and down here you're going to have less. So it's going to be the change. It's not going to be your absolute potential energy. That's going to be like extremely large. It's our change in potential energy. That is going to be completely equal to the wind force that is applied here. So that's going to be our work of wind. Okay, so our initial kinetic, to change these into equations, we'll do it like this: 1/2 mv squared plus mg times delta h, the change in height, and that's going to be equal to 7,500 joules, because that's what we calculated as the work as done by wind. Okay, cool. So given this, we just need to solve for v. Okay, so let's do some algebra ASAP fast to solve for v. So I'll actually go back to writing WW just to make this a little lighter. To write minus mg delta h is equal to 1/2 mv squared, multiply both sides by 2 over m, equals 2 over m of WW minus mg delta h, and our velocity is just going to be this whole thing under the square root. Okay. Copy pastas, definitely helpful. Okay, so subbing in our numbers here, we are going to have 2 over Jane's mass, so 50 kilograms, multiplied by the work done by the wind, 7,500 joules, minus Jane's mass, so 50 times 9.8. And this is the change in height, so we have to find... so it's really just going to be like 14.3 minus 5 equals 14.3 minus 5 meters. And that is 9.3 meters. Okay, hopefully that's what we calculated here as well. I'm going to assume that's going to be caused by a rounding error, but it's pretty much the same. They went with Pythagoras. I mean, it's close enough to where I'm just going to assume that that's a rounding error, but we'll go with 9.3. So times 9.3 meters, all under the root. Okay, so let's math that out ASAP fast. Okay, so under the root we got 2 divided by 50 multiplied by 7,500 minus 50 times 9.8 times 9.3, all under the root, and I calculated the initial velocity needed to be 10.85 meters per second. Okay, so initial velocity required to cross the river. Okay, cool. So that would address part A. Came to the exact same number here. That's awesome. It's just like the way that this question is set up is kind of spooky, but we'll talk about that later. Okay, so part B of this question is asking us, now they're trying to go backwards. So Tarzan and Jane are trying to swing back to go the other way. Okay, so what is the minimum speed that they need to make that possible? So now we got this, now we want to set up the equation in a different way. So part B, still the same situation, the same setup, the same forces and everything. So here, let's pay attention to the wind. The wind is going towards the right. So in this case, the wind is going to be helping us. And we're also going to try to arrive with a zero kinetic energy. Okay, and we also need to keep in mind we need to increase our potential energy because we are getting higher up. So all of our kinetic energy is going to be converted into gravitational potential energy. So really what we have here is our initial kinetic energy plus the work done by wind is going to be equal to our final potential energy, or our change in potential energy, which is mg delta h. Now keep in mind here, now we have both people on the rope now. So our mass is going to be 50 kilograms of Jane plus 90 kilograms of Tarzan, for a total of 140 kilograms of friendship. Cool. So let's turn these equations into, or turn these symbols into equations. So here we got 1/2 mv squared plus the work done by wind is equal to mg delta h. Should have wrote potential energy. Whoops. Nothing to worry about. And we just got to isolate for v once again. So we shall have v is equal to, under the roots, we have 2 over m multiplied by mg delta h minus the work done by wind, all under the root. Okay, cool. So let's sub in our numbers. 2 over our combined mass, so that's 130 kilograms, times 130 kilograms, times 9.8 meters per second, times our change in height, which was 9.3 meters. It's the same change in height, minus 7,500. That's the amount of joules, the work done by the wind. So let's calculate this out and see what we get. Okay, so under the root we got 2 divided by 130 inverse, divided by 130, my bad, times, in brackets, 130 times 9.8 times 9.3 minus 7,500, close the bracket, and my result for this is 8.18 meters per second. Velocity required to return. Okay, hopefully we came to a similar conclusion down here. About 8, I'm going to assume that these are just rounding discrepancies. Or I am actually tripping by writing 130 instead of 140. Jeez. Luckily in my calculator, that's a very easy thing to recalculate. That's very bad of me, so very stay ready to avoid things like that. And yeah, I did actually calculate 8.66 as well. Per meters per second, and that would be the velocity required to return across that chasm. Okay, so I would call this a question complete. My only concern is some of these equations are set up funny, but otherwise everything's good. So equations are set up funny, but otherwise the correct solution is found. Nice. Oh man, so that was the last question that we have. Unfortunately, time flies when you're having fun, as the old saying goes. So those are all the questions that we have today. If you enjoyed today's Q&A and would like to be notified of when we do this again, please hit the subscribe button and ring the notification bell below. Yeah, ring the notification bell and subscribe if you really enjoyed the video. If you're interested in submitting your own questions, please visit the links in the description below. Leave a like and a comment, and if you really enjoyed the video, share it with your friends. This has been Millen from OneClass. Today was a great time with the physics. I hope you have a great day, and I hope to see you again soon on our next OneClass live stream. Take care and have an amazing night, or day, or afternoon, whatever time it is for you. Enjoy yourself, enjoy the physics, and stay safe and take care.